All right, let's see the steps of the design. After you have the cooling load, then you know how much is the total CFM. For example, here you can first calculate the total CFM of the whole system. For every section, then you will have, for this case, is 6,000 CFM. And then the second step is you select the velocities of various duct sections. It is to be reminded again that the biggest velocity should be at the entrance. And please use the table that is shown on the next slide. Alright, here we know that the main duct, the recommended velocities for the main duct is 1,000 to 1,300 feet per minute. However, in the table also stated that for the main duct, the maximum velocities for the main duct is between 1,100 to 1,600 feet per minute. So you can select actually any velocity within this range. For example, here in this case we choose 1,400 feet per minute. And we should also see what is the maximum velocities for the branch duct. For in this case, for public buildings, for branch duct, the range is between 800 and 1,300. That means the lowest velocity at the end of your duct is minimum 800 feet per minute. You cannot be, the velocity cannot be lower than 800. Alright, so actually you can choose any velocity. For example, from B to C, the velocity that you choose is 1,400, and then from C to D is like the previous slide, couple of hundreds, I mean, but not less than 800. For example, you choose 1,100, and then from D to E you further reduce the velocity to 1,000, and E to 7 maybe 800 or 900, and E to 6 maybe again 900 or 1,000. The main thing is you have to keep the range in check, and also the velocity should be reduced as it goes further from the entrance, and the lowest velocity should be at the end of the duct system, and in this case is from E to 7. Yeah, this is the recommended velocity for this example. From E5, D3, C1 you select 900, and for section 56, 34 and 12 you select 800 FPM. Alright, by using duct calculator, as I said before, if you know the CFM and your velocity, then you can determine your duct size, whether it is round or rectangular. But in our case, normally for rigid duct we choose rectangular because it is cheaper when the client doesn't give any specification, or the pressure loss is not that important in the system, then yeah, you really have to take every factors into account. If the pressure loss, you need lower pressure loss, but of course the cost will be higher, and so on. Because if you have the money, then why not? And after you know the size, from ductilator you can also read the friction rate or the friction loss for the section, for the duct section, and please multiply with the respective length, because in the question you are asked to calculate the friction loss for the whole length of the duct section. Alright, so this is an example, a table example. Here you can put on your left, you can put in the first column the notation of the duct section, and the second column is the capacity in CFM. This one normally it is already given, and the third column is velocity that you choose. Again, I want to remind you that in this column you need to check the allowable maximum velocity range for the respective buildings, for the type of the buildings. And the fourth and the fifth column is actually the size of the duct. One is for a round duct and the other one is for rectangular duct. And it is again to be reminded that the width, if possible, the width must be greater than the height. And at the end, for the last one, is a friction rate in water gauge per 100 feet that you can actually read from the ductilator according to the size that you choose. You can adjust the size so that you will have the lower friction rate, if possible, if the cost allows you. Alright, the second method is the equal friction method. Due to its name, the equal friction method, equal means the same. That means for the whole duct section, if possible, you use the same friction loss. Normally, in industry, some industry use 0.1 water gauge per 100 feet, and some other use 0.15 inch water gauge per 100 feet. Well, it depends. If it is not stated, then for our exam, we just use 0.1 inch water gauge per 100 feet. Alright, and this chosen friction loss rate in inch water gauge per 100 feet should be maintained, or must be maintained, should be maintained throughout the system. Where it's not possible, then you are allowed to use the velocity reduction method. And the design friction loss rate depends on allowable velocity in the duct. You have to cross-check with the allowable velocity also. For example, in public buildings, how much is the velocity allowed? If the friction loss that you choose result in a certain duct size, and after you check and if you read from the ductilator, the velocity exceed or less than the allowable velocity of the duct, then you cannot choose the friction loss rate. Sorry. Alright, so basically the typical design eco-friction loss ranges from 0.08 to 0.15 inch water gauge per 100 feet of duct. It depends. So this is an example. You should determine the rectangular size for each section of the system by using eco-friction method, and the capacity of airflow is as indicated in the figure, and this is an industrial system. So you need to check what is the allowable velocity for an industrial system, both for the main duct and also for the branch duct. Alright, the step 1 is also the same like velocity reduction method. First you need to see what is the total CFM for the system. This one you know from the cooling load that you calculated before you design this air duct system. And for this example, we have 9,000 CFM. And if you check from the table, just wait, the friction rate is okay, from the friction table for 9,000 CFM, and also you cross check the main duct. The allowable velocity is the maximum velocity for the duct, for the main duct for industrial buildings is 2,200. And if you take your duct calculator with 9,000 CFM and 2,200 feet per minute velocity, then your resulted friction rate is 0.21 inch water gauge per 100 feet. And for industrial building, you can see for the main duct, the minimum velocity for industrial buildings is 1,800, and the corresponding friction rate, if you check with the duct calculator, is 0.125 inch water gauge. So now you have your friction rate or friction loss rate between 0.21 and also 0.125. So this is the range. Now you can choose any friction rate value within this range. Yeah, for example, in this case, we choose 0.15 as recommended normally in an industry. And we held this value, we use this value throughout our entire system. Let's say this system is a normal system. There's no special case, no chemical used, and so on. Alright, the second step is you have to fill in the flow quantities and the design friction rate in the table. And by using your duct calculator with known CFM and your chosen design friction rate, you can find the size of the round duct diameter, and also you can choose your rectangular duct size. The step 4, you can calculate your airflow velocity in each section And as we know, the formula for the airflow velocity is equals to Q over A. You can check in the earlier lecture. And step 5, fill in the result table. And this is an example of the table for equal friction method. The first column on your left, you can put your duct section notation, and the second column you can put the capacity or CFM for each section, and for design friction rate in inch water gauge per 100 feet. This one is the value that you choose between the range, the resulted range from the known the known velocity and also the CFM. In the fourth and fifth column, you have your chosen round duct size and also the rectangular duct size. And at the end, you will have your velocity. And in this example, actually there is no there is no fixed answer. You cannot say that your feet per minute is 1596. You can just round it up to 1500 or 1600. Just round it up. Never use a specific answer like this. That's why I put it in red. Alright, whatever methods that you use, it requires some engineering judgment and extensive manual recalculation. So you cannot say that if your system is better than other engineers for identical solution. You may have different solution than other engineers, and the resulted thing is you will have different size of components, different fans, different duct size, will incur different costs, and also the overall system energy demands. This depends on your design, but you should keep in mind that you should design the system, if possible, the lowest cost but the most effective one, of course. Alright, that's all from me. Thank you for listening, and see you in the next lecture. Thank you.